Now, I'm sure you've seen games like this being played in shops, and you've probably bought one or two for yourself to play at home. And you may have wondered how easy it is to write an arcade game like the one you were just looking at in BASIC. Well, the answer is that almost anything that can be done in machine language, which is the language that was written in, can be done in BASIC as well, but it'll be a lot slower. So although you can write quite fast and quite interesting arcade games using BASIC, you've got to be realistic about the amount you can expect the computer to do at a time. But as long as you stay within reasonable limits, you can get some quite good games written. And that's what we're going to set out to do during this videotape. Let's go back and look at the screen to see what aspects we're going to need to look at. Now, we have various things on the screen. There's a certain amount of fixed scenery. There are objects moving by themselves without our control. And down here, when we press keys on the keyboard, we have an object that is under our control. And we also have a score and maybe various other numbers that are part of the game. So we'll need to look at the ways of producing each of these within our basic program. And we'll start by taking a very simple character, just in a single color, and seeing how we can move it around the screen under the control of the keyboard. Well, this coding will define the shape of the character and the position on the screen. Well, I've started by using mode 2. And although this only gives us 20 characters across a line, so it's not very good for text, it does give us all the colors possible. And so this is the mode we normally use for games. I have a Vdu 23 statement, which is defining the shape of character number 224. These 8 numbers following simply define the shape of that character. And it's a small ball. But of course we can change that to whatever shape we want. The print statement prints at tab 10, 15, that's 10 characters across and 15 characters down, the character whose number is 224. That's the one whose shape we just defined. So let's start with these 3 statements in our program and see what they do. There's character 224, a small ball shape printed in the middle of the screen, at the position we specified with tab. Well, that's not much use. For a start, we want to be able to move it around. And while we're doing that, why don't we change its color as well? So let's add some more lines of coding. Well, for a start, I've put in a color statement. So all our printing will be done in red. I've changed my print statement so that instead of using constant values, I've used variables, x% and y%. And you'll remember these are 2 of the resident integer variables. I've used them for speed. I set x% to 10 and y% to 15. And now in line 40, I've said x% equals x% plus 1. So that's going to move our symbol 1 space to the right next time we print it, because line 50 simply goes back to the print statement, prints the character again, but of course this time x% is 1 bigger, so it should print it a little bit to the right. Well, let's see the result of running that coding. Well, 2 problems. The first one is that when I printed the second position for this little character, I should have rubbed out the first one. We've ended up with a complete line of them instead of one moving across the screen. And the second problem is that as soon as I reached the right-hand side of the screen, my print tab was invalid, and so the character was then printed down the left-hand margin. So we always need to check to make sure that the character we're moving doesn't go off the screen. Well, let's add some more lines of coding to rub out the character as we move it, and to make sure that we don't go outside our screen area. Now I've made some more changes to this coding. Let's go quickly through them. Down here, where I was increasing x% by 1, I've changed it to use a variable. I've called it move%. And I've had to put two O's in the middle because, of course, move is one of the basic keywords, so we couldn't use that for the name of a variable. And I've set its value initially to 1. Now, these statements, 50 and 60, are checking the value of x%. If x% is greater than 19, that would mean we'd gone off the edge of the screen. So I've said, put x% back to 19 and change move% to -1. So as soon as we've reached the right-hand side of the screen, we'll change the direction of movement and come back. And line 60 does exactly the same job for the left-hand side of the screen. If x% is less than 0, then set it to 0 and make move% equal to 1, so that we're now moving back in this direction. Now, as well as my original print statement, to print my character at location x%, y%, I've added a further print statement. Now, this is printing a space, and I'm using this to rub out the character when I want to put it in a different position. I'm still using y% because we're only traveling horizontally at the moment. And I've used ox%, meaning old x%. I've set the value of ox% here to be x%. So as soon as I've printed my little ball, I've remembered its position in ox%, so that here I can rub it out with a space before I go back to print it in a new position. Well, let's see what the result of running this coding is. We have our ball bouncing happily backwards and forwards between the two sides of the screen. And notice that I've got rid of the flashing cursor. And I did that with a Vdu statement, which you will see at the top of the screen. Another Vdu 23 statement, this time not being used to redefine a character, as this one was, but Vdu 23,1 being used to turn the cursor on and off. And you'll see that described in your user guide. Also, note that we do have a for statement here. For i% equals 1 to 100, next. This is just a little loop that will go round and round 100 times, not doing anything. The only reason I've got that in the program is to slow it down. At the moment, the program is so small and we're doing so little with it that if I let it run at full speed, it will be almost too fast to see. But let's have a look at it without that delay loop. As you can see, it's zooming backwards and forwards almost too fast for the screen to keep up with. So we'll slow it down again, and then we'll put in some controls so that we can control the way it moves by using the keyboard. Now, I've had to put a lot more statements into this coding, and so I've renumbered the program. And also, I won't be able to show you the whole program on the screen at one time because it's got too big. But don't worry, because we'll record all this coding onto the soundtrack of the videotape at the end of this session. And you'll then be able to copy it into your own computer. So let's look at the first set of changes. As well as move%, I've got y-move%. So move% is going to control me left and right, and I'll use y-move% to allow me to move up and down. As well as ox% for the old value of x%, I'm using oy% for the old value of y%. Now, statement 90, $G equals $get. $Get will allow me to type one character at the keyboard. And that character will then be put into my character variable, $G. Remember, with get, I don't have to press return. As soon as I've pressed one key, the value is put into my variable. I now have 4 if statements, testing for 4 possible values in $. And I've used Z and X for moving left and right, and colon and slash to move up and down. And if you've played many arcade games, you probably know that these are the commonest keys for moving around on the screen. If I pressed Z, then I decrease 1 from move percent. This means that I'm going to be coming back this way. If $G is X, if I've typed an X, I'm moving this way. If $G is a colon, then I'm changing Y move percent. Y move percent equals -1, means I'm going to move 1 character upwards. And similarly, a slash means I'm going to move downwards. And then whatever value I put into move percent and Y move percent, I'm going to use them to change my X percent and Y percent values. Well, let's see how that works. Well, there's our ball in its starting position. And if I press the colon key, it moves up, slash, it moves down, Z for left, and X for right. Now, the speed at which it moves is controlled by the speed at which the keyboard repeats. And you'll notice there's a delay. It moves up 1 character immediately, pauses, before it continues going upwards. And the same with the slash to move it downwards. Now we can change this by using fx calls. Now fx statements or fx calls are not really part of BASIC. They're instructions to the operating system of your computer, but we can use them within BASIC programs. And what they do is give instructions to the operating system about the way the computer is going to work. Now we're going to use 2 fx calls which control the way the keyboard repeats. And we'll be using some more later on to control the way that the flashing colors flash. Well, let's look at the 2 we're going to use now, fx 11 and 12. Here you see at the beginning of the program, I have 2 lines of coding starting with asterisks. And when BASIC finds a line starting with an asterisk, it assumes that it's going to be an instruction to the operating system. So the whole of the rest of the line is given to the operating system, and BASIC doesn't look at it anymore. fx11 controls the delay before a key on the keyboard repeats. And fx12 controls the speed at which the keys repeat. Now the number following is the number of 1/100ths of a second before these things happen. So fx 11,100 says, when I've pressed a key, don't make that key repeat until 1 complete second has gone by. fx 12,100 says, as the key is repeating, repeat at 1 character per second. Well, that's very slow, but it will allow us to see how they're working. Let's run the program with these 2 extra statements in and see the result. If I now press the X key to move right, you can see I'm moving 1 position each second. And the same with the colon key used to move upwards. Well, that's obviously far too slow. So let's change those 2 fx calls to give us a much smaller delay. Well, I've now reset these values to 5. This means that it will only take 1/20th of a second before automatic repeating starts and between automatic repeats. Well, let's see what effect that had on our little bouncing ball. can see it's now moving quite a lot faster. And we're not yet at the limit because we could try and speed it up even more. If we reset them both down to the smallest value, that's 1/100th of a second between repeats, you'll be able to see the result. It's moving almost too quickly for us to control. Well, that's given us the first of our requirements, to be able to take a shape and use keyboard controls to move it around the screen. We've seen one way of reading the keyboard to achieve this. Now we'll take a break there and we'll record all that program onto the soundtrack of the video cassette. From there, you can copy it to your own audio cassette and load it into the machine and use it yourself. I put an extra statement on the front which will program function key 0 to reset the repeat rate for the keyboard. So if you use the program, press escape to terminate it, and then press function key 0, that'll reset your keyboard to normal. And after the break, we'll look at some more complicated programs, ones which can create multicolored shapes and move them a little more accurately around the screen. Now, as our computer is capable of handling several different colors at a time, it would make sense to try to create a character that contains several different colors. Well, let's see what happens when we try to do that, using the coding I've got here. Now, in this procedure, I've got a whole series of Vdu statements. 4 of them are Vdu 23 statements. They've been used to define 4 separate characters, and I've used numbers 240 to 243. And the other 3 statements are Vdu 19 statements, and you'll remember those are used to change the relationship between the logical colors, in this case 1, 2, and 4, and actual colors, and I've changed them to colors 8, 15, and 11. Now what I'm going to try to do is combine together these 4 characters using different colors into a single character position to give us a multicolored character. Well, let's start by looking to see what each of these 4 separate characters looks like. Now I've gone into mode 2 so that we can see the characters full size, and I've printed out each of these 4 user-defined characters. And here you see them: a large diamond, a medium-sized diamond, a small diamond, and a dot to go in the middle. And what we're going to set out to do is to print 4 of these all in one character position, but in different colors, to give us a multicolored character. Now, because we're going to be doing a lot of printing of characters, I'm not going to use print and the char dollar function. I'm going to use the Vdu statement, because as long as we know the number of a character, we can use the Vdu statement to print it very simply. So let's look at the same coding, but using Vdu statements. Now each of these numbers is going to be sent to the screen as a single character. There's our 240, 241, 242, and 243. Before them, I'm sending a 13, which is a carriage return, meaning come to the left-hand side, and 2 10s. And 10 means a line feed, or move down one line. That's given me a little bit of extra space here, before the characters. Similarly, 2 more line feeds and a carriage return afterwards. I put them into this statement partly to space this out a little so that you could see our 4 characters, and partly to remind you that we can put all sorts of control characters into a VDU statement, as well as characters that we're going to print. We'll be using this facility in just a few moments. So, VDU 240 by itself would just have printed that large diamond at the current position on the screen. So let's go back to our program and see how we can try to combine these 4 characters. Well, there's the procedure we looked at a moment ago, defining our characters and setting up colors. And we call it here in line 20, Proc define. I then done a print tab to the middle of the screen. Then for each of the 4 characters I set a different color, colors 1, 2, 3 and 4, and used a VDU statement to print the character. Well, let's see the result of running that. Here are our 4 characters. The first 2 are printed in flashing black and white and flashing white and black. So they keep appearing and disappearing. It's quite a useful facility using the flashing colors. There's the 4th one, which is flashing yellow and blue. The 3rd one is in a fixed color. So we've got our 4 parts of the character printed in 4 different colors. What we need to do now is to overprint them, one on top of the other. Well, let's try putting a backspace into that coding to see if it works. Well, I've changed the coding by adding an 8 to each of these VDU statements. If you check in your user guide, you'll see that VDU 8 is a backspace, move back 1 character position. So what we're doing is printing character 240 and then backspacing, printing 241 and backspacing, 242 and backspacing, 243 and backspacing. Each of the characters being printed in a different color. Well, let's run that and see what happens. The answer is nothing. All the characters were printed here, but of course each time we backspaced and printed another character on top, the character that we just printed was overwritten. We can't do our printing in character mode. We're going to have to print these characters in graphics mode. This means we'll have to do all our moving around the screen and all our selection of colors using the graphics commands and not the text commands, because our characters are going to be printed at the position of the graphics cursor using the current graphics color. So let's see what changes we need to make to the coding to achieve this. The 2 new things in this version of the coding that you need to look at are here, a statement saying VDU 5, and here another one saying VDU 4. And these 2 statements, VDU 5 and VDU 4, are used to switch between these 2 types of printing, printing in character mode and printing in graphics mode. And I think I can show you a little more clearly the effect of printing in graphics mode with a more concrete example. Now, printing a character in text mode is like using paper. Here we have our foreground color, and that's opaque. But also, the background is opaque. If we put this character down onto our screen, then everywhere that's the foreground color will be seen, in this case, in green. Everywhere else within the character will be seen as the background color. But printing in graphics mode is rather like drawing on a piece of clear plastic. If we overprint with that, then these 2 spots, the foreground color, can be seen. but the background color doesn't cover up what was there before. It's transparent. And so we get the two characters combined. We could take a third character and overprint with that as well. Again, the foreground color can be seen, but the background doesn't obscure what was there before. So because we've started here with a VDU 5, our print tab has changed to a move, and our color statements have changed to GCOL, graphics color. We set the graphics color and do our VDU 240 and the backspace. Change the graphics color, print the next part of the character, and so on, printing the 4 different parts of the character in its 4 different colors. And VDU 4 at the end to make sure that we return to normal text printing. Well, let's see what happens when we run this version of the program. There we have it, a single character, roughly in the middle of the screen. And you can see how the 4 component parts have all been overlaid into a single character position. The reason it seems to be pulsating, getting larger and smaller, is because the outer 2 diamonds, you remember, have been printed in flashing black and white and flashing white and black. Now this version of the coding might look very similar to the other, but in fact there's one important difference. I've taken away my GCOL statements, my graphics color statements, and replaced them with more numbers in my VDU statements. And this is the first step to simplifying this coding. Again, this is something you can check in your user guide, but you'll find that VDU 18 has the same effect as GCOL. So 1801 in a VDU statement gives me the same effect as GCOL 01. So what were 4 GCOL statements and 4 VDU statements can be converted to 4 longer VDU statements. And we could, if we wanted, extend that to combine all these numbers together into a single VDU statement. But we can simplify it in a different way by taking all these numbers and putting them into a character string and then just printing that character string. Here's the main part of the program, and now between our VDU 5 and our VDU 4 we simply have a move and a print. Print $, because into $, I've put all the information necessary to print that composite character, both the color changes and the different shapes. Well, the work for that has been done in Proc define. So let's have a look at the coding in Proc define. Well, most of Proc define is the same as before, our VDU 23s and 19s. This is the new part. I've put in 2 data statements containing all the numbers that were being used in those VDU statements. I've set up a new variable called $, and I've started by setting it to the null string, just 2 quotation marks side by side. So $, starts with a length of 0. There are 20 numbers whose VDU codes I want to send, and so here I have a little loop going from 1 to 20, reading these numbers one at a time using a read statement, reading J%, and then adding to the end of $, the character whose number is J%. So as I go round this loop 20 times, I'll take these 20 numbers, convert each of them to the character with that number, and add them to the end of $. So at the end of this, $, will be a 20-character string. and its characters will be character value 18, character value 3, character value 1, and so on down the list. And the program still does exactly the same thing, as we can tell if we run it. Well, the next thing, of course, is to persuade this shape to move on the screen. And here I have a repeat until loop that should make it move. I'm printing $, then I'm using a plot 0, 8, 4. If you don't remember, you can check in your user guide, but plot 0 is a relative movement, relative to where we are at the moment. That's move 8 pixels to the right and 4 up. So as we go round and round that loop, we should continually reprint our shape in an upwards diagonal line. Let's run it and see what happens. Well, that wasn't quite what we expected. And of course the reason is the same as with our original coding with the bouncing ball. We're printing our character, and then before we go and print it again in a different place, we really ought to rub it out. Now, of course, we can't just print a space over it, because we're in graphics mode, and printing a space would have no effect. So we need to use an alternative technique. And to see what I've done, let's look closely at those data statements. Now, you remember that the 18s in these data statements were for Vdu 18, which was gcol. And the two numbers following the 18s are the two numbers we'd put in gcol. Now, the second number is the color number, 1 and 3, 2 and 4. But the first number, which I've got as 0 in these 4 gcols, means the way in which the color is plotted. And a 0 simply means put that color on the screen, irrespective of what was there before. Now I'm going to use a different number now. I'm going to use 3. Now what gcol with a 3 as its first number means is to plot the color onto the screen, but exclusive ORing that color with the color that was there before. Now this is explained in your user guide, but you can use the technique quite simply even without understanding the mathematics behind it. If you're interested, check it up in the manual. But let's make that change and see what the effect is. Running the program gives us this, our little shape moving as we expect it to. Here's the beginning of the program, and within our repeat until loop, we now have 2 print statements. They're both printing $, but the effect of one is to cancel out the other. We start with a single print, which will print at position 50, 50. We then enter the repeat, and this print, which will still be in the same position, will rub out the result of the first printing. Our plot then moves us a little bit right and a little bit up, and we print again in the new position. Going back to the repeat, this print will rub out our character before we move on to the next position and print it again. And that's the effect of gcol 3, of using exclusive OR. If we print something and then print exactly the same thing in the same place again, everything is back as it was. No matter what color was underneath, that color will be restored when we print again for the second time to rub out. And we'll see this technique used quite a lot when we have moving graphics. The next thing we need to do with this shape is to be able to move it around the screen under the control of our keys. And as you can see, I've modified the program so that it'll do just that. Notice also that it's able to move in 8 directions: straight up, left, down, right, but diagonally as well. So the technique I've used this time for reading the keyboard to decide which way I'm going to move is a technique that's able to read more than one key at once. Let's have a look at the statements I did that with. Now here you see the change I've made to the repeat until loop. I still have my 2 print statements, but I have a procedure reference in between them, proc key move. And that's the procedure that reads the keyboard to find out which keys I'm pressing in order to decide where to move my shape. So let's have a look at proc key move. Here's our move statement to position ourselves to x%, y%, the coordinates that we want the shape at. These 4 if statements use the in key function. Now we can use in key either with a positive value or a negative value. If we use it with a negative value, we're actually asking to see if a certain key on the keyboard is pressed down at that moment. -98 asks about the Z key. If that gives a true result, that means the Z key is being held down. -67 is the X key. -73, colon, and -105, slash. So I've used exactly the same 4 keys to control my shape as I used earlier. But this is without actually reading a character from the keyboard. This is just checking to see if a certain key is being held down. If the Z key is being pressed, I subtract 8 from x%. If the X key is pressed, I add 8 to x%. So I can check on all 4 of these keys in one pass through this procedure and adjust x% and y% according to which ones have been held down. Now having a shape on a blank screen isn't much fun, so let's add a background. There's our shape. There's a very simple background around it, and as you can see we can drive our shape over the background without changing it. Remember, using G-call3 allows us to replace whatever was underneath the shape when the shape moves on. By printing the same shape twice, we make sure that the background is unchanged when we reprint in a new position. We should perhaps have a look to see what coding was used to create that background. Of course, it was done in a procedure. Let's have a look at it. Proc background draws that line of skyscrapers along the bottom of the screen. Let's just see how it does it. 2 Vdu 19 statements, setting colors 5 and 6. And then a loop, for next. X% is going from 0 up to 1200 in steps of 120. So each of those blocks will be 120 wide. Y% is being given a value of 300 plus a random value from 1 to 500. This allows the skyscrapers to be of different heights, and they'll be different each time we run because of this random factor. And we're also choosing a random color. Graphics color 0, 4 plus RND 3. So that'll give us a value of 5 or 6 or 7 randomly as we draw the blocks across the screen. Here we have 2 move statements and 2 plot 85 statements, which together will fill in the complete rectangle. And we do that all the way across the screen before we start moving our shape around. Now this version of the program is very similar, except that instead of simple vertical bars of color at the bottom, we've got random blocks of our three different colors. But there's one very important difference between this program and the one before. And I can show you that as I drive my shape around. All the time I'm going on green or blue, there's no effect. But as soon as I hit the white, the program can tell that I'm on white. In this case, it's making a simple noise using a Vdu 7 statement. So as I travel around, I've been able to work out whether my shape has collided with white or is traveling completely on blue and green. And this idea of a collision is very important, because most games that involve shapes moving around the screen have to make decisions at one time or another to work out whether two shapes have met or are still separated. So let's see how I decided what color background my shape was traveling on. Now, the four crucial statements involved in working out whether we're traveling on white or green or blue are these four. Four if statements testing the value given back to us by the function point. We give two values to point, and it tells us the color number at that point on the screen. Color 7 is white. So I'm saying if the point whose address is X%, Y% is color 7, I've crashed. Now, why do we need 4 tests? Well, that test looks at the color of the point at the top left of my shape. The next statement looks at the point at the bottom left. That one is the top right, and that one is the bottom right. So I'm testing the color of the background at each of the 4 corners of my shape. And if any of them is a 7, meaning that corner is sitting on some white background, I call the procedure proc crash. And for the moment, as we haven't looked at sounds in detail, proc crash simply contains a Vdu 7 statement. There's a subtle difference between this version of the program and the one we looked at a moment ago. For a start, there's one red block, because now we have an objective. We have to take our shape down to the red block and change it to a white block. A red block will appear somewhere else, and we have to move, avoiding the white as far as possible, to change that. And we'll also see a score. Each time we cross white, we'll lose points. Each time we hit the red block and change its color, we'll gain points. Let's see how it works. You see the score has appeared. As I cross white, my score goes down. I've hit the red's disappeared and reappeared on the other side of the screen. If you're not used to playing arcade games, it can be quite difficult to get all your fingers working in the right direction at the right time. But you'll see how it's developed into quite a reasonable start for a game. Here's our main loop again, and we've added a line of coding here and a line here. This one switches back to Vdu 4. This means we'll be printing at the text cursor and not the graphics cursor. And that line is just used to print the score. S% contains the score, and there's the word score. Print tab, of course, works when we're printing in text mode. 0, 0 will be at the very top left of the screen. As soon as we've printed out the score, we do a Vdu 5 to take us back into printing at the graphics cursor. And we have an extra test here, again using point, as we did with those 4, to see if we were on white. But this one checks for color 9. Color 9 is set to red. The coordinates I'm giving here are of the middle of our shape, rather than the corners that I used for the crash. If it is equal to 9, if we've managed to hit the red block, we go to procedure proc hit. Proc hit does three things. Firstly, it adds 100 to our score. And then it uses another procedure, proc block. 7 and 9 are colors. The 7 is used to change the red block to a white block by redrawing it, and 9 is used to draw a red block somewhere else on the screen. And you can look at the details of those procedures when you copy the program into your own computer. Well, we'll break there, and as before, we'll record this program onto the soundtrack of your video cassette. Now, do take the time to copy it into your own computer and look at the coding that's been used, because we've covered several new facilities and several new techniques that you're going to find useful when you sit down, design and write your own graphics programs. After this break, we'll come back and we'll look at some sound statements. Well, I don't think the Electron is going to replace the piano, but there's a fair range of sounds and sound effects that we can get out of it. And so I'd like to show you just a few of the ways in which you can program sound and program effects of various kinds to go with your games. Let's start with the basic sound statement. Here's the simplest sound statement, and we have 4 values here. A channel, which I've set to 1, a volume, which I've given a value of 15 to, but notice the minus sign. The volume has to be specified as a negative value. Pitch, I've given a value of 100 to, and that can have a value between 0, the lowest note, and 255, the highest. The time is the length of the note. A value of 20 will give me a note of 1 second duration. So, what does that sound like? A 1 second note of moderate pitch. Let's try it again using a different value for the pitch. Here I have 2 sound statements. The first time I'm using a pitch of 0, and the second one will use a pitch of 255. So that's the lowest note and the highest note that you can get. Now in this coding, I've put a for next loop. I'm using the same sound statement, but I've set the time to 1, and I'm varying the pitch from 0 to 100. So this will play 101 notes, each of them very short, but of increasing pitch. And if we wanted the pitch to rise more quickly, we could put a step into the for statement, playing fewer notes, but with the difference in pitch between them being greater. Here I've used a step of 4, so we'll go up 4 times as rapidly. Let's listen to that. It goes up more quickly, and you can hear the individual notes. Now let's have a listen to channel 0, the channel for making noises with. In this coding, I've changed the channel number to 0, and I've increased the time to 20, so we'll get a second of each noise. Notice that the pitch is only going from 0 to 7, because there are only 8 basic noises we can make with channel 0. Let's have a listen to them. Four buzzes and 4 hisses. But by programming them carefully, we can get some very interesting effects. Now in this coding, I've got a 4 next loop again, but this time with 2 sound statements. I'm still using channel 0, but I've set the duration, the time, to 2. That's 1/10 of a second. And I set the pitch to 5, which is one of our hissing sounds. Full volume on the first of these statements, but 0 volume, which will give me silence in the second. I'm doing that 20 times. Let's have a listen to that. And by changing the duration of these notes and the pitch we used, we could use that sort of effect to represent almost any sort of machine, steam engine, helicopter, drill, whatever we liked. Let's have a look at one of the buzzing noises. Here, I've changed to using pitch number 2, and I've shortened both my times down to 1/20th of a second. Let's listen to that one. Again, a noise that very easily gets incorporated into many different sorts of game. Now we might want a noise like this in one of our games. And we could get that by using coding that looks like this. I've got to repeat until false, just for this example, so that the noise will continue forever. And I've got 2 4 next loops. Each of them contains a sound statement. I'm using channel 1, volume -15, and a time of 1 in each case. I'm using I% for the pitch of the note. And in my first 4 next loop, I% is going from 100 up to 110, and in the other loop, it's going back down from 110 to 100 in steps of -1. So that gives us this up and down wailing noise that you just heard. But the problem with that is that it's taking the program all its time to create that noise, and so it wouldn't have time to do anything else. But we can get that sort of effect by changing the sound statement to use what the Electron refers to as an envelope number instead of a volume. This little 2-line program should give us the same sound effect as we heard a moment ago, but with certain extra advantages. Here's our sound statement, and the important thing to notice is this second number. I haven't put a negative value, meaning a volume. I've put the number 1, and the Electron will interpret that as meaning envelope number 1. Now you'll find the details of all these different numbers in your user guide, because the envelope statement is quite complicated. So I'll just explain what I'm doing with this particular one. I'm asking the Electron to go up 1 step of pitch 10 times. And when it's done that, I'm asking it to go down 1 step 10 times again. So the pitch will rise by 10 steps and then come down by 10 steps. And it'll repeat that over and over again. This second number, the 4, controls the speed. Well, I've got it going quite fast. The fastest would be 1. Well, let's listen to that. As you can hear, the sound is almost exactly the same as the one we heard a moment ago. But we can change it a lot more easily by changing these numbers. For a start, let's speed it up. Let's take that number 4 and reduce it to 1. There's the envelope statement using a 1 for the time, and let's see what that sounds like. As you can hear, the pitch is rising and falling much more rapidly. In fact, we can make quite complicated sound patterns by adjusting the numbers in the envelope. I'll give you one more example now, and then we'll record some onto the soundtrack of this video cassette for you. Believe it or not, all this is coming from a single sound statement, of course with the correct envelope. Note also that there's a prompt there. This means that I could still continue writing a basic program, listing it, or this music could be part of another program, because the sound is produced by a separate chip, which can run on by itself without the main part of the computer. Let's stop it and have a look at the envelope. A little more complicated. I've slowed it down so that we can hear the individual steps as the pitch changes. The steps are up 8 pitch units, down 12, and then up 12. It's going up 8 5 times, down 12 3 times, and then up 12 once. And then it's repeating it again. Well, that's all we have time for on this videotape. I hope you've learned something about the use of graphics and the use of sound in your programs, and that you'll look at the programs we've recorded on our soundtrack following this. Until then, good programming.